Hi, this video will cover week 7 of the class NCBM 0114, which is a co-requisite for the class Math 1314 Pre-Calculus 1. What we're going to cover in this section is how to find the domain of a rational function, and also how to find the asymptotes for graphing purposes. So what we're going to do here, well, first, let's see if we can fill in the blank. So the domain of a rational function is any number except the x values that will cause the denominator to equal 0. And the reason we have to exclude those numbers, we have to find those x values so that we can exclude them from the domain, is because if we were to divide by 0, then we will get an undefined solution. And at that point, the graph is just not going to go across that x value. In fact, it will have a vertical asymptote or a discontinuity in the form of an open circle. So one of the first things we have to do is, well, the question here is to find the domain. So first thing we do, we take the denominator of the function and we say that cannot equal to 0. So this will be x cannot equal to positive 5. And so if we want to write down the domain as an interval, it will be from negative infinity to 5 without including 5. So we use parentheses, and then we use the union symbol, parentheses, 5 to positive infinity. And that's it for that question. Find the domain. So any real number except for 5. Now the next one, we're going to approach it the same way. So we're going to take what's in the denominator, which in this case is a quadratic function, or a quadratic expression, I should say. And here we could solve it two different ways. One of them will be to, well, first of all, we say that cannot equal to 0. So we could factor this. It is a difference of squares. So it will be x plus 5 and x minus 5 equals 0. Now from here, if you have your factors equaling 0, you could solve for each factor. You can take each factor, equal it to 0, and solve for x one at a time. So x equals negative 5. And for the other factor, which is x minus 5 is equal to 0, the x value will be positive 5. So right there, we're going to have two exclusions. So we're saying x cannot equal 5 or positive 5. Another way to solve it, I'll do it here real quick. It will be to have that does not equal 0. We take the negative 25 across. So it will be positive 25. And then from here, we could take the square root on both sides to undo the square. So this will give us x is equal or does not equal positive and negative 5, which is the same thing that we got here. Now to write it as an interval, it will be negative infinity to negative 5, parentheses, union, negative 5 to positive 5, parentheses, union from 5 to infinity. And that's the end for that problem. Now on the next example, we're still going to find the domain. So we're going to use the same method. We take the denominator, and with that, we say that cannot equal to 0. So if I was to take that positive 25 across, it will become a negative 25, or subtract 25 from both sides. Now, to undo the square, we need to take the square root. And so right here, we're going to run into some issues because we cannot take the square root of a negative number. And so if you put that on the calculator, it will say error, or it might say something like undefined, or it might say something like no real solution. And the reason for that is because you will need to have imaginary numbers, which we will cover in chapter 2. So no real solutions. And from there, what this means is that for the domain, there are no x values that could cause the denominator to equal to 0. And so therefore, there are no exclusions to the domain. So the domain will just be all real numbers. Now for the next problem, we're going to use the same method. So we take this denominator and we're going to factor it. It is a trinomial square, so we're going to factor it into, or try to factor into the product of two binomials. So in this case, we're going to get x and x. This sign is negative, so that means that we have a positive and a negative sign here. And then we're going to have a 4 and a 5. Those are the factors of 20. The 5 will be negative, and the 4 will be positive. Why? Because negative 5 plus 4 is equal to negative 1. And that's what we needed here, negative 1x. So now from here, we take each factor, set it at not equal to 0, and then solve for x. So we get x does not equal to negative 4. And for the other one, minus 5 does not equal 0. So that would be x does not equal positive 5. Now that is how we exclude numbers from the domain. Let's just write the answer as an interval. So from negative infinity, we always start from the smallest to negative 4. We use parentheses because that means negative 4 is not included. Then union from negative 4 all the way to 5. Parentheses again because 5 is not included. And then union from 5 to infinity. And that's it. That would be the answer for that question. Now we're going to move on to the next topic, which is vertical asymptotes of rational functions. And so since we already know how to find the domain or find those x values that will cause the denominator to equal to 0, then those same numbers that we exclude from the domain are going to form the vertical asymptotes, which are the vertical lines in the rational function graph. So some of the ways for us to find them, of course, is we take the denominator. In this case, you equal it to 0. You try to factor if possible. Then you simplify common factors, and then you identify the zeros of the denominator, all those x values that will cause the denominator to equal to 0. Now here we're going to have to factor because what may look like it could cause a vertical asymptote on the function. If we factor and we're able to simplify, that will not all the exclusions from the domain will become asymptotes. Some of them so whenever we're not able to simplify or cancel out a factor from the denominator, that exclusion will still be a vertical asymptote. However, if we're able to cancel something from the equation, we are going to get an open circle, or we call them holes, or it could be also referred to as a continuity. And that will occur whenever we're able to cancel things out. So let's get to the examples. I'm going to go to the next page. So right here, we need to find the vertical asymptotes. So in this case, I'm going to do the same process I was doing with domain, but instead of saying does not equal, I'm just going to say equals 0. Then I'm going to factor it as the product of two binomials. So x plus 1, x minus 1. Why can I do that? Because That is the difference of squares. Once I get to this point, I take each factor one at a time, say that equals 0, and then we solve for x. So x equals -1 and x equals +1. Those two will be vertical asymptotes. Now, if we look at the next function, function g, before we find those asymptotes, we're going to try to factor this function. And so the denominator can be factor difference of squares, so we can find x plus 1 times x minus 1. And so what will happen here is that since we are canceling the whole x minus 1, all of it together, we can do that. So now this function happens to be, we have to put something on top, so that will be a 1 over x plus 1. So this is what happens. The only vertical asymptote will come from that factor that was not canceled. We equal it to 0 and we solve for x, so x equals -1. However, the factor that was canceled, which we could refer to as a removable discontinuity, will be x minus 1 equals 0, so x is equal to 1. And so what will happen there is the graph will not have a continuous line. At that value of x equals 1, it will have an open circle, which means not included. Why? Well, because if the question was just find the domain, we will still have to exclude the x value that gives you the vertical asymptote, but also the x value that gives you the removable discontinuity. The fact that that is part of the domain makes us graph it and put an open circle there to indicate that that is not an actual value of the graph. However, since it was factored out and simplified by canceling with this x minus 1, that's why we don't graph it as a vertical line or vertical asymptote. Now let's move to example 4. Now for example 4, if we try to solve this equation, taking the denominator equaling it to 0, it will say x squared is equal to -1. Now, in imaginary numbers, yeah, it does have a solution. It will be plus minus I, and we will cover that section pretty soon. But however, if you put this in the calculator, like taking the square root, you're here, and if we take the square root here and here, we will get x, and then the calculator will say no real solution or error. And what that means is that there are no vertical asymptotes. And that is okay. In fact, this function yes, no vertical asymptotes. It would still have a horizontal asymptote because it is bottom heavy, and that will be y equals 0. But vertical asymptotes it will not have. And that is okay. Now, the next one, let's see if we can factor it, because something's telling me that we might be able to cancel something. So this will be x and x. We need a plus and a minus. Factors of 21, we have 121. We have 3 and 7. And we need a positive and a negative. So right here, I know that if I use positive 7 and negative 3, I will get positive 4. And so that's how I'm going to place my factors here, positive 7, negative 3. And because of that, now I am able to cancel those factors, x plus 7 on top and x plus 7 on the bottom. So now what happens there, my RD, removable discontinuity, comes from x plus 7 equals 0. So x is equal to negative 7. So when you graph it, that point will appear as a hole or an open circle. That came from this factor. Now the other factor says x minus 3, and that's what's going to give me my vertical asymptote. And that will be x is equal to positive 3. Now, if we go back and the question says, what is the domain? We will still exclude negative 7 and we will exclude positive 3. We must exclude both of them, the whole and the vertical asymptote. Now, let's move on to horizontal asymptotes. And for this one, we have 3 cases. We have here case 1 that says n is less than m. So what I want you to notice is that we're using the letter n to denote the degree of the numerator, the top. And we are using m to denote the degree of the denominator, so the bottom. So whenever the degree of the bottom is greater than the top, I like to refer to those as bottom heavy. Rational functions. Then whenever the top, the degree of the top is greater than the degree of the bottom, I like to refer to those as top heavy. So this is case 1, case 3. And let's see what case 2 will be. So now case 2 is saying that the degree of the top and the degree of the bottom is the same. So I like to call those same degree. So based on that, we're going to have 3 ways to find the horizontal asymptote if it does exist. So whenever we have something that is bottom heavy, by default, the horizontal asymptote will be the line y equals 0. Whenever we have a function that is top heavy, by default, there is no horizontal asymptote. So bottom heavy, the horizontal asymptote is y0. Top heavy, no horizontal asymptote. What about same degree? So for same degree, we're going to use the leading coefficients and we're going to create a ratio, or we're going to divide them. The coefficient of the numerator, the leading coefficient from the numerator divided by the leading coefficient from the denominator. A rational function can have no horizontal asymptote or one horizontal asymptote. The graph of a rational function can cross a horizontal asymptote. So that is okay. However, if it was vertical, those are not crossed. So let's complete the last example, 5 and 6. So it says here, find the horizontal asymptote. So here we have the degree of the top is a 2, the degree of the bottom is a 2. That tells me is this rational function is of same degree. Remember, to determine the degree, we look at the highest exponent. So because of that, the horizontal asymptote is going to be the ratio of the 2 leading coefficients. So we're going to divide them. And those numbers are 9 and 3. So 9 divided by 3, so that will give me y is equal to 3. That is the horizontal asymptote. The next equation, it happens to be bottom heavy. because the degree of the bottom is a 2, the degree of the top is a 1. So default here, the horizontal asymptote of any bottom-heavy rational function will be y equals 0, unless there's a vertical shifting going on. So that easy. Next problem, still, we need to find the horizontal asymptotes. And so right here, we have degree 3 on the top, degree 2 on the bottom. So we refer to this as top-heavy. And if you look back at your notes, you will notice that top-heavy has no horizontal asymptote. And that's it. That's the answer. Our last problem of the day, we do have same degree. Degree on top is 1. Degree on the bottom is also a 1. And so in this case, the horizontal asymptote is going to be y equals, and we're going to take the ratio again of the leading quotients, with those being -2 and +3. -2 and +3. So then my horizontal asymptote will be the line -2/3. And that concludes the video. Thank you for watching.